Hello, I am Dr. Zenya Worth, and in this video, we will be discussing definite and improper integrals. We will start with definite integrals, and we will finish with improper integrals. Definite integrals allow you to find a numerical value for the area under a curve bounded by certain integration limits. In this case, we're using integration limits a and b. So you have a curve f of x, as seen in this figure here. And then you want to find the area under that curve from certain points, and those points are the integration limits. In this case, we're also bounded by the x-axis, so finding the area between f of x and the x-axis. Let's do an example. Let's find the area of a space bounded by a certain function f of x and the x-axis. We define the limits of integration as 0 and 1, and our function f of x is 2x minus 6x to the fourth plus 5. If we take the integral of this, we take the integral of each of the polynomials under this expression. So remember our rules for integration, it's the opposite of differentiation. So in this case, instead of subtracting 1 from the exponent like we do in differentiation for a polynomial, we add 1. So x to the 1, we would add 1, that becomes x squared, and then we divide by whatever that new digit is as your polynomial, or the degree of your polynomial. And we leave our constants in front of our x alone. So we don't actually do anything with the 2, we leave it alone, but we add 1 to the degree of the polynomial here and divide by whatever that new degree of the polynomial is. So in this case, the integral of this expression would be 2 times x squared over 2 minus 6, leaving the constant alone, times x to the fifth over 5 plus 5. This is actually 5 times x to the 0 because x to the 0 is equal to 1. So that just becomes 5x. And then we apply the limits of integration here. Since this is a definite integral, we now have integration limits 1 and 0. So we're actually finding the number by plugging in our limits 1 and our limit 0 for x and subtracting the two quantities. So we start here and we plug in 1 for our value of x for every time we see an x in the expression. And from that, we subtract the same expression, except instead of plugging in for 1 for the x, we plug in 0. So that's 1 squared minus 6 over 5 times 1 to the fifth plus 5 minus, well, there's an x in every one of these polynomials, so that's 0, 0, 0. And we end up discovering that the area under this curve is 24 over 5. Let's do a slightly more challenging example. So in this case, we're not bounded by the x-axis anymore, but it's an area that's bounded by two separate curves. We have on top, or bounded above, we have y is equal to x plus 2, which is a linear relationship, or linear function. And then below, we have y is equal to x squared, which is a polynomial function. This area is going to be bounded by 2 points. And those 2 points are where the parabola intersects the straight line. So that's going to be the limits of our curve. But we don't know what those are, we need to find them. So we first need to find those roots by setting the two equations equal to each other, because that's where the parabola intersects the straight line. So x plus 2 is equal to x squared. I move all the terms to one side and factor, and I find that these two curves intersect at x is equal to 2 and x is equal to negative 1. So these are going to be the boundaries of our area, and these are going to be the limits of integration. Then we integrate. The other thing we need to do when we set up our integral here is we need to determine which of these two expressions, y is equal to x plus 2 or y equals at x squared, which one comes first and which one comes second in the integral. Since we're bounded above by x plus 2, that comes first, and then we subtract what we're bounded below, or what is being bounded by below. So below, we are bounded by x squared. So we subtract x squared from x plus 2, and that is our integration from negative 1 to 2. So again, we have our polynomial here. We apply the rules of integration, and we find that the integral there is negative x cubed, or over 3 plus x squared over 2 plus 2x, and we apply the limits of integration. First, we substitute in 2 for every value of x here, and then we subtract the substitution of negative 1 for every value of x. And as we do that algebra, we find that the area under this curve, bounded by both of those curves, is 9 over 2. Let's move on to improper integrals now. Improper integrals cover both integrals that have infinity as one or more of the limits of integration and integrals that are discontinuous over the integration limits. We're going to start by addressing infinity, and we're going to have a little review here. Let's review some general expressions as n approaches infinity. So some general functions here. If you take the limit of all of these functions as n approaches infinity, Most of these converge to a certain value, 100, and this one actually converges to e to the x. So here's just some review for you here for how we approach infinity and take the limit as we approach infinity. If we integrate something over an unbounded interval, it will either converge to a certain value as we extend the limit to infinity, or it will diverge. If, as we take the integral to infinity, if something approaches a finite value, then the improper integral is said to converge. Otherwise, if it does not approach a finite value, the improper integral is going to diverge. So what we do here is we take the limit from as b approaches infinity from a to b of whatever function that we have here. So if we have a function that has an infinity as an integration limit, in this case, let's say it's where b is, instead of trying to apply that definite integral with infinity as an integration limit, we substitute a value of b in here, or we actually put a placeholder variable in there. And then we take the limit as that placeholder variable approaches infinity. So we start by taking the integral here, and we have b as a placeholder limit of integration for our infinity value, and then we take the limit as b approaches infinity. If that converges to L or converges to a certain value, then that integral will converge. Otherwise, that integral will diverge. We can do the same thing as we approach negative infinity. So in this case, we're taking the integral of negative infinity to b of f of x dx, and we put a placeholder value a in for negative infinity, and we take the limit as a approaches negative infinity of this entire function. So that's what we're going to do, and I'll show you a couple examples of how we do that. Here are some examples of just improper integrals that you might come across. The integral from 0 to infinity of e to the negative 2x dx equals 1/2. So if I do the analysis, it equals 1/2. So that converges to a finite value. Same thing for the integral from 1 to infinity of 1 over x squared dx. However, the integral from 1 to infinity of 1 over x dx diverges. It does not converge to a finite value. And a lot of times our trigonometric functions, when we take the integral, those tend to diverge as well as we approach infinity. So let's do a little proof here to demonstrate. So we have the integral from 1 to infinity over 1 over x squared dx. So I'm going to put a placeholder in here. Instead of having a limit of integration that's infinity, I'm going to put b there. And I'm going to take the limit as b approaches infinity of the integral. The integral of 1 over x squared is negative 1 over x. And we're going to evaluate that at limits b and 1. And we're going to take that whole expression and take the limit of that expression as b approaches infinity. So if I substitute b in here, I get 1 over b, negative 1 over b, minus negative 1, because that's my limit of infinity. And I find that the limit as b approaches infinity of this solution to the integral, 1 minus 1 over b, actually converges to 1. Because as b gets larger and larger, this expression will disappear, will converge to 0, and this entire expression will converge to 1. So that's why the limit from 1 to infinity of the integral of 1 over x squared dx is actually equal to 1. Now let's look at a different example. Let's look at 1 over x dx. The integral of 1 over x dx is ln of x. Same thing, we substitute b as a placeholder in for infinity and take the limit as b approaches infinity. ln of b minus ln of 1 is after applying the integration limits, and ln of 1 is 0, it goes away. So now our final expression is the limit as b approaches infinity of ln of b. And that actually equals infinity. So this is going to diverge. Now let's move on to a different type of improper integral that has a discontinuity over the integration limits. A discontinuity is a break in a curve where there's an abrupt change in a function. It can be a jump, it can be a piecewise function, or some sort of essential discontinuity. Unfortunately, the value of these discontinuities are not the same as you approach the function from the negative and positive directions, or if there's a gap. The integral of a discontinuous function must be evaluated by taking the limit as we approach the discontinuity. So we need to actually have the discontinuity as part of our limits in order to effectively solve. So this becomes a little more friendly if the discontinuity is already the endpoint of the limits of integration, because we know that the function will be discontinuous at that point. It's already in the limits, and we can solve it using the limit equation. In this particular example, we have the integral from 0 to 3 of 1 over the square root of 3 minus x dx. Well, if I substitute 3 in here, this becomes 1 over 0, which is impossible to analyze. So this is a discontinuous function because we cannot analyze it as the function approaches, or as x approaches 3. So since this upper limit of integration 3 is not definable, we again substitute some dummy variable in. It can be t, it can be a, it can be b, whatever number or whatever letter you want. But we add some dummy variable, and we take the integral as that dummy variable approaches the limit of the discontinuity. So in this case, the discontinuity is not infinity. It is some finite value that makes the limit, or it makes the integral impossible to analyze. So in this case, since we know that 3 is going to be our problem limit, we put a t in here for 3, and we take the limit as t approaches 3 of whatever this integral is. We take the integral first, so the integral of this is actually -2 square root of 3 minus x, and we evaluate that from the limits 0 to t, and take that limit as t approaches infinity. T approaches 3, sorry. So if we substitute in t and 0, we end up with this expression, and we take the limit of this expression as t approaches 3, and this is going to go away, because if you substitute 3 in here, this is actually going to go to 0 and disappear. So the limit of this is actually 2 square root of 3. So this is actually the solution to this improper integral, and the integral is going to converge to the solution because the limit exists and approaches a finite value. These problems become slightly more complicated if the discontinuity is not actually one of the integration limits here. If it's not one of the endpoints, but it's somewhere in between, we have to recognize that it's there and take multiple integrals. So let's look at the same example here, but now my problem number 3 is actually embedded within this function, within these limits of integration, but it's not the endpoint. In this case, we're going to have to split up the integral at the point of discontinuity, and we're going to have to take 2 separate integrals and approach that limit, or that point of discontinuity 3, from both the left side and the right side. So we're going to do this by creating 2 separate integrals and evaluating them independently. I'm still going to substitute t for the limit, or for my integration limit. I'm still going to evaluate it at t, and I'm still going to find the limit as t approaches my discontinuous point, which in this case is 3, and find the solution. So we did this one already. So we already know that the solution to this is 2 square root of 3. But what happens when we take the limit, and we take the integral from 3 to 5 over this function? So I still have the same solution to my integral. It's still -2 square root of 3 minus x. But in this case, I'm evaluating at the integration limits 5, and t is my lower integration limit in this case, because the limit as t approaches 3 is going to be the lower limit here. I evaluate this integral now using my new integration limits, and I find that this converges to -2 square root of -2. So this limit converges, and so does this one. They do have a finite value. So this is actually the solution to my integral. I'm going to add the 2 solutions together, because I'm going to add the 2 integrals together. And I find that the actual solution to the integral from 0 to 5 of 1 over the square root of 3 minus x dx is 2 square root of 3 minus 2 square root of -2. So this is an imaginary number, but it is not, but it does exist and converge to a value. So here's another example where the discontinuity is embedded in the integration limits. So I have the integral from -3 to 3 of 1 over x squared dx. This is not continuous at x is equal to 0. So we need to split up the integral at that point. So we have 2 integrals now, the integral from -3 to 0 of 1 over x squared dx, and the integral from 0 to 3 of 1 over x squared dx. So I evaluate both of those integrals. First, I evaluate the integral. Then I set up a dummy variable to approach whatever discontinuous point I have. I set the limit to approach that from the left-hand or the right-hand side. And I try to determine the value of that limit. In this case, as I approach t is equal to 0 from the left-hand side, I approach infinity for the solution. And if I approach t is equal to 0 from the right-hand side or the positive side, I approach -infinity. So since this is happening, the integral is going to diverge. And that is going to be your solution. The improper integral diverges. I encourage you to try some of these practice problems. The first one is a definite integral that should be fairly friendly to analyze from the integration limit 0 to 5. So you're finding the area under this curve. The second 2 are 2 examples of improper integrals, one that has an infinity as a limit of integration, and one that is discontinuous at some point in here. So please try to evaluate these in practice. And hopefully that will help you review definite and improper integrals. I hope you find this video useful in your class.